So, basically, I'm still in the ward, the CG project. So, today's date is Saturday. One second, guys. Today's date is 21st of February. Saturday, 21st of February. Saturday, the 21st of February, 2026. The time now is 6:10 p.m. So this is my journal. So I've got here on TV the linkable, unlinkable, linkable density format. But don't worry about this video. I'm just doing my review, a standard review process. So this is one reality that happened in there. I normally go to a review like this, guys, review reviews.
你心里的历史书本销售，记得关注我的专业知名的课，
So this is basically the link. I want you guys to have this free of charge. So basically this is the guest to the page. But I'm just showing this. So what this video is some magnetic memory. This is magnet. So so basically I just want to say the point of this video is to explore the kind of magnetic memory model. So you have a gravity model, gravity model, who I call the graviton model, because it's magnetic. So if it collapses, you get if it's you have an orbit, so you have celestial bodies which are called planets. And you can have a planet, a sun, a moon, but these planets are packages. So you can have a planet which is tridimensional. So the planet represents the messages. Let's say you have three planets, three protons, and they are spinning around. They're entangled. They're spinning around each other. So one proton is here, another proton is here, one proton is here. This moves a proton, but this moves a proton. This comes another proton. You have a celestial orbit, so you can have them going like this, guys, spin around each other. Spin around each other. So they have a common center. They all share like this, or like this, or like this. But there was one second. There's two atoms, but basically this remove I'm holding because the message, and this cup is another message. But these are two tridimensional messages. You can have a third one, but it's like juggling. It's basically juggling. Yeah, with three objects. So if you have one in the center, and one in the x-axis, one in the y-axis, you can have a science because it's African science, but it works. So let's just stick with two for now. But the two have a three, so you're gonna have a combination. You're gonna have one goes left, one goes down, one goes up, one goes down. But the foliage is and one goes left, one goes right. One goes front, one goes back. And one goes an angle, one goes an opposite angle. So you're gonna have the one goes for an angle, and one goes for an opposite angle. These are the two. So really goes to Z, X, Y, Z. So I'm saying to you guys, this is what the magnetic memory does. It goes to have them collapse into the center when it's sent. So you're gonna have two halves of a sense. Okay, mate. So you're gonna have two halves. So you're gonna have one divided by epsilon equals equal divided by epsilon, which is growth factor of E. You can have force equals K times V. K times V, K times E. E is the basic K times E. E is the S is the stiffness. No, look at me, mate. I'm recording. Please look at me. I'm not understanding. Sorry about that. So so you're gonna have that system. So basically, you also have a boomerang. So when you throw a boomerang, it goes like this, and it comes up to the center, come into your hand, or come up to the area, the region where your hand's gonna be. But you got things like wind and everything that makes it go offset. So the wind, the gust of wind affects it, but it's not perfect. So the boomerang is perfect. Even though basically, the boomerang when you flick, you have to flick a boomerang. You don't basically it's not a vertical launch. It's a side launch. You have to launch from the side. So if it's like you just throw it, if it's just means throw it over arm, or you put on the arm, so you can throw it on the arm, you can throw it over, that's the same thing, or even opposite thing, you can throw it sideways, you have to throw it at the angle sideways. But if there's no wind, on a perfect day, the boomerang will come to your hand, back to your hand. So it's a boomerang model of the message. So the message is basically for magnetic messages. So for the symbolic for the food, giving you food or the shelter. Because if the protocol over the system is compound, basically it can enforce the protocol itself. It's like, so if I send you a message, that message is already received. It's good because basically it works on magnets. For example, we got theta 45 degrees, theta is 45 degrees, and 45 degrees is the measurement of the system. So if you have 45 degrees, you have to modify 45 degrees. So you have basically, if you have modified, you have 45 degrees, you have minus 45 degrees. And that would be the opposite side of a system, But that opposite side represents a system's 45 degrees, So it's really the same principle we're talking about, So 45 degrees, you have a polarity. So you have 45, you have minus 45 degrees. So basically, you have a span between, you have a processing area of minus 45 to positive 45, which is basically 45 plus 45 is 90. 90 plus another 90. 90 plus 45 is 5, 9, 10, 11, 12, 13. 9, 10, 11, 12, 13. 135 degrees of a search space of processing space between two polar angles, 45 degrees and 45 degrees. Now, that will be theta. That will be theta of x, y, and z. They share that set space. So theta x will be equal to tan inverse tan. Basically, inverse tan is a measurement of the frequency of the system. It does one divided by tan. You get 1 divided by e, 1 divided by e, 1 divided by e, 1 divided by tan, 1 divided by cosecant, and 1 divided by secant. To the power of negative, no, 1 divided by the cosecant times b to the power b divided by a, where b is row pitch. Well, don't come here, Joe. Can't see you. Where pitch is the b is the displacement over the rotation, over the angular rotation. Because you go row, which is the row of a row pitch. So b is the displacement, row, and a is the magnetic property of b. So you gotta contain polar form to Cartesian form to calculate this model. So b divided by a, where a is the imaginary unit, a sub I. So a is an angle of I, where I is a complex number. I is the square root of negative 1. So that's how that works. I'm going to compute, I can put my calculator here so I can compute it for you guys. But that's the goal. So, it's magnetic. So you gotta have two poles at all times for magnetism. So if you have the root and these are protons. Now, protons, when you do a single slit experiment, you have a proton, basically, you observe a particle and the wave. But the wave is basically because the slit has interfered with the trajectory of, so you're gonna have two forms of but you don't have a medium. So I'm hypothesizing that light goes protons don't just go through medium and diffract. So you separated the medium. So you have a medium of a slit, and that is this is the proton. So the proton is really on the other side as a wave. And proton is wave. You get like a wave form of a wave. You're gonna have the wave form and the teleported form, which is the proton on the other side. So you have two things happening. So you're gonna have the proton being on the other side of the experiment. Also, you're gonna have two kind of wave formats. So you're gonna have a proton propagated as a wave and a proton propagated as a thing. Well, this is the two models. So the proton represents a light wave, a light format, like electromagnetic wave, like a LED light, like a LED. But if I have a LED light, I'm talking about the color red. Now, red, I send the color red through a slit. Now, that slit will be a red hue. Give me a red hue, saturation and lightness. So basically, that color can be distilled into can be distilled into a wave format as it propagates downwards, down the. It can just be on the side, But understand. So that's a single slit with now double slit segment shows basically for double slit you have two mediums. So you have 2 points. You're gonna have a wave, this construct. You get a smaller waveform, two small separate waveforms, and 4 dots. So basically, the waveform projects away. You get two for the single slit. Well, remember, you get 2 outputs. So for the single slit, you have one wave, one output, two outputs. So the 2 outputs is collapsing into one, which is the message. So you cannot destroy the message. I cannot get the message back. It's basically in a different format that the resolver can always see. Basically, the measurement frequency of the system is basically if I have a proton and I have something and an observer of a proton, let's call it an observer of a proton. Then the proton observer will literally be observing the proton, and the proton will be seen. So if I'm here and this is a proton, I'm observing the proton and it has a spin, I can't see it. I can't, it doesn't render. It's there. It's doing this proton thing because he has power. He has been one of this proton basically represents something that can something at a point of light, a light point, a light ray. it's looking. I'm pointing at it. So the more I go closer to this light, the more it measures me. It takes a measurement of me. But I know, sorry, I take a measurement of the proton. Sorry, because I'm seeing the proton. So I take a measurement of the proton. The more I'm closer to it, so basically, I'm just taking a measurement. It's constrained some kind of angle. Angle. So basically, it's able. This proton can say what I'm moving forward and backs. Go back too. But yes, the declare system. The root system. If I flip it, or if I put it actually, if I have the proton, and proton is a red, so I can just by taking the red color now, the wavelength. Okay, let's just say white color, white color, like the white, and then and then can paint me a picture, perfect picture of a projection of me. What I say is important. This is important. So. Okay, let's go red. So the red would be like a red quantified with red. So it would be like a red hue, which would be like me, like moving about, basically my movement, basically in that space for that. So basically, if it's a red leg, really like basically, and the red legs on my head, my face only, or on my body, and this is my body, but I can't see it's invisible. The ray, basically, they can see me. Someone on the other end of this ray can see me. Someone holding this ring can see me. You can see a perfect hue. So it's hypothetically, I know that because you got a hue here, so the hue will be someone behind the proton, so someone shining, someone this person. So the observer of this proton will see me, but I cannot see them, because they're taking a full measurement of my I'm taking a full measurement of my reality. So basically, it doesn't matter where it's coming from. This can be ultraviolet night light, but they can basically the night light can be like night vision goggles. Because as long as I have the visual, so as long as I am making the movement, as long as I'm taking the measurement, I am being seen, I am in that space, I didn't want to take measurement because basically, as I look more, I go to the proton, which is the light right there. I add to the measurement, so you can have me be measured as called a forward and backwards auxiliary measurement. So this is called auxiliary Eigen vector because I don't have to define that ahead of time. I don't have to define the how I want to go, where I want to go. I just have to go that place. But the pathway is constructed for me. So, for example, let me give you an example. Pi over 4 is north for 5 degrees. So if I have pi over 4, I have half pi, but I have pi over 2. Pi over 4, if I have a half of pi, which is pi over 2, I'm facing, okay, pi over 4, so I want to go north.
Can I do your hair in
No,
your beard?
no, 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 later.
When?
Because I'm busy, Tess, I'm recording.
Oh.
Don't
Hi.
call, no.
Hello.
Tess, do science.
Oh.
I didn't even know that you were
Should we have a dance? Come on.
I'm doing science, Tess.
Du-
You
du- du- du-
know it's going to be on YouTube.
Right, do you want... No, don't. Don't put me on
YouTube.
YouTube.
Doesn't want you to be here.
I want to do your hair and your beard.
Yes, please, Tess, later.
When's later?
Can you do one of it?
You know I can't.
But Tess, you interrupted me. Tess, I need you to focus. I need to focus, okay? So basically, the proton is static, it's measuring you. So you're constructing. So it doesn't matter what the situation is. If I go forward, the proton will be red, but the red hue will be a measurement of me step red. So think of it as pi over 4. I'm going north, but the red will be a different hue, obviously. So you can construct when I go north, east, south, or west. Just pretend this is the current angles of it. Basically, north is downward, somewhere in the east and south. So that's north, east, south, and west. So if I go north here, north, and proton is here, it's taking a measurement, it's taking control. So it doesn't. This is about granular control. Granular control. Basically, if I have, say I want a computer to go 2 units forward, 2 units forward, let's say 2 feet forward, 2 feet forward, 2 feet, 2 foot forward, 6 feet forward, 6 foot. 6 feet, 2 feet forward. That's 2 steps. 2 steps. 2 feet forward is 2 steps. 2 adult steps. So if it goes 2 steps forward, it's gonna need the computer to go 2 steps forward divided by 5. So let's say 2.5 steps forward. So 2 steps forward is 1, 2 from the center, which is your reference. So 2 steps. So it's about vertical. So 1, 1, 2. Now I'm 2 steps north. Now, basically, you have rotation. Say if I rotate from north, for example, so I'm moving north, for example, it's 90 degrees here. This is, I go 1, 2. Now, I'm here. Now, I'm here. 45 degrees. Now, I'm here. Can you see my body? Now, I'm here. So, now I'm here at this spot. I should be facing that way. I'm still pointing this way. But if I let's say go a half, backwards, a half, but there's no referential point. There's no, it's just the center will be magnetic. So the center will be decided already. So the center is basically where the planet's oriented. So this is where the planets were so before. So if I was here and the new center, basically there's an absolute center. There's a relative center. And this is where I stop. And I go 1, 2, 2 feet north. 2 feet north, 5 degrees, 2 feet north. Oh, I'm going clockwise. So I turn clockwise. I'm going to go anti-clockwise. Then you get my 5 degrees, you get my 5 degrees, 2, 4, 1, 2. I get my 5 degrees. So this 5 degrees is here. These 2 spaces here. So the spin is these 2 spaces, but the frequency will be yeah. So basically, you're gonna have 2 times 45 degrees and minus 45 degrees because you have 2 angles, you have 2 poles, and the 2 poles are 2 separate entities of that planet. You know, they are quantum superposition. They are entangled because they have a relative center. You know, so basically, they have 2 fluids, and you're gonna have that's very important to remember. Remember that. So you're gonna have 2 halves of the system in orbit, 2 halves of the system. Then you're gonna have those 2 steps, then not take a half. Now, so I don't have to compute a half because I have to do 1 step. So first of all, it's a gradual control and recomputation problem. So if I have 1 half of step, that's 1 child foot step forward. So this is my stride, this is my half feet, you know, and that's a child's foot. So that's how. So if I take 2.5 step, 2.5 step. But you get a vector, so you're gonna have 2.5. So 2.5 will be 2.5 steps. So it can be either 2.5 steps forward or 2. Then you complete a half of 2. That will be 2 divided by 2. 2 divided by 2. 2 divided by a half, or will be 1.5. No, 0.5. Like a half of 2. What's half of 2 divided by 2 is 1. Is a half. So that would be half. So you can have 2 representations. So basically you have a topographic layer to the system. So you're gonna have 2.5. So you're gonna have 2.5 or half of 2. You know, half of 2. So let's do half of 2, and that will be 2 divided by 2 will be half. 2 divided by 2 divided by 2 will be 1 divided by 0. 1.5. No, that's 4.5. 0.5. Half. 0.5 times 0.5. 0.75. Anything is a half. So basically, you can compute half vectors, quarter vectors. So 2 times a half will be 2 times 2 is 4. 2 times. Basically, you're gonna have 2 times 2 divided by 1. So 2 times 1 is 2. Divided by 2 is 1. So you're gonna have 1 over 2. You're gonna get 1/2 of the system. So you're gonna have 1/2 of the system. Because you're gonna have the improper fraction of the, so you're gonna have the conjugate of the product, which is gonna have divide by division. But the conjugate is already in the system, so you just have to take a measurement of the conjugate. So after the system to get the system in this. So this is what. So I'm gonna end this video. So this is where we go. The units are why I made auxiliary vectors is because they compute things in space, and this space doesn't is geometric. So this is why it makes so basically I'll do my review today, and so basically it's auxiliary computation. Basically you're gonna have Eigen vectors. They measure nothing or something. It has auxiliary vectors. It's called auxiliary vectors because they will the real world polar rules. Thank you guys for watching. You can just turn it off.